decided to give a talk about an overview of the type of things I do. So there will be not much details. I'm not sure if it was a good idea, but let's try. So I hope it will be useful. So basically, I am going to talk about three things. One is related with neuroscience and neuroimaging on a statistical method for analyzing networks. And then I'm going to talk about some stochastic modeling related with criticality. Okay, so when you think about networks, typically most of the literature is based on individual network analysis, but at least in the physics community. But if you think in neuroscience, where a network is, let's say, a brain, we will have a lot of networks. So we want to concentrate in the analysis of a sample of networks or an ensemble of networks. So the typical question is how to compare this if you have two populations, let's say group A, group B, and you have functional networks, or it doesn't matter if they are functional or are structural. You have some subject with its network, and the point is how to compare. And in the area of neuroimage, some years ago, some paper appears that many of the results are not very reproducible. So we start to work on looking some robust methodology. So the point is how to compare this, or if you have only one subject under two stimulus, and in each stimulus you have different networks, you want to know if this stimulus have any effect. So given a sample of networks, one thing that we are interested in is in how to define a central network and how to measure the variability, how to detect an outlier. Outliers can have important effects when analyzing data. How to do hypothesis testing or supervised or unsupervised learning. And all this can be done if you define a distance between two networks. G1 is one network, G2 is another. If you define a distance, the typical distance is what is called the distance, that it just measure the number of different links between two networks. So the distance is one if they differ just in one link. And this is our framework. Given a distance, we can do all this, and now I'm going to show you some examples. So choose randomly a subject here and put it in the scanner. Now what we have is a random network. And the space of networks is huge. For example, if we have just 7 nodes, the number of possible networks is 2 to the 21. But in order to define a central network, we can compute what is the expected distance from a random network to a given particular graph. For example, let's say here I have the graph H, and G is a random network. So in order to compute the expected distance from this graph H to any random graph, just you compute the distance between G1, G2, Gn, and you multiply by the probability of observing this graph. But once you have an expected distance, you can say, as in dimension 1, your center is the one that minimizes this distance. So if you want to find what is let's put this in this way, the problem. You have 100 persons, okay, choose the brain of one that is in the middle, that is the most representative of them, and then what you have to do is to minimize the expected distance, okay? The one that minimize, if you are not familiar, in dimension one, the mean minimized the expected distance, the square expected distance, and the median minimized the expected distance. Okay. If you have a center, you can now compute the variability. You have two populations. The variability of the populations are the same, are different. Then you just compute the distance to each center, to each central graph. And if you have data, you just change the expected value by the average. Okay? Let me show you an example. If we are in dimension one, we have just not a double exponential distribution that is centered around x0, okay? So the expected distance, the expected value here is x0. And now we can do the same with graph. We say there is some particular graph that will be called as 0, and there will be an exponential decay with the distance that is here. And now we want to compute what is the central graph given this probability law, and what we obtain is what we expect, that this S0 is the central graph. Okay, how to detect outlier detection? How to detect outliers? This is very simple. If you have a distance, an outlier is the one that is very far, and very far is the one that have an average distance to the rest of the graph big. So in this case, in the context of neuroscience, maybe what is the atypical brain network or non-healthy. So if you compute this, you will find some graph that have a large distance. And finally, if you have a distance, you can first do a hypothesis testing. Perhaps many of you are familiar with what is an ANOVA test, or for two groups, Wilcox or not t-test. That is when you have one unique variable. Now we don't have variables. What we have is networks. But in a similar way, we can compute distance between groups, distance within groups, and define some statistics in order to measure if the populations are the same or not. Okay. This is the particular statistic that doesn't matter, but the point is that when you have, let's say, this detection problem, you have 100 brain networks, another 100 brain networks, you compare and you say, okay, my p-value is very small, so you detect that there are differences between the groups. Now you can ask, okay, which is the subnetwork that shows the highest difference between the groups? And what can be done is just to find a subset of links or a subset of nodes that minimize these statistics. The point is, in a network, you can have difference because just one particular region have differences, but and the other the other parts of the network, it's like putting noise. So if you erase the noise, you will have greater differences. Okay, so this is just to present some methodology for analysis networks. There are many types of networks, not only in neuroimage. So I invite you to, if you have sample of networks, to think about this methodology. And now I'm going to talk something about modeling that I've been doing. The first is related with universality classes. Here we have two models, the Erdos-Renyi model on a random graph. I don't know if you are familiar with that. Basically, we have n nodes, and each one connects with probability p, independent of each other. And you study the size of the Young component. And when you study the size of the Young component in the limit of n going to infinity, you see that there is this particular behavior for if the mean degree, the average number of links that has one node is less than 1, then in the limit, the size will be 0, the size of the Young component. And from 1 on, this increase as the expected degree minus 1 to power beta. And here we have the model, the percolation, that with probability p, one side is occupied, and you study the same. What is the same? The size of the Young component, and you see that you have like a similar scaling. Okay. Now, the point is these two models are in the same universality class. In order to know that, we have to analyze in detail the scaling of both models to know if they are in the same class. Okay? Now, I'm going to put another question that is, it would be nice to have, let's say, I have a model here, and I would like to generate another model in the same universality class. This, I think, would be nice. And that is the question that is here. Given a model, how to construct other models within the same universality class? So I'm going to try to attack this question for a particular model. And this particular model is a fusion particle model. The model is very simple. We have in a one-dimensional space particles that can move to the right or to the left with different velocity, and when they collide, they fuse, and there is conservation of momentum, and it's a plastic collision. Okay, but if we have 3 particles, not 2, then the number of final particles in this example will be 3, because this will fuse, and then this will go to the right, and this to the left, and we will have 1, but we can have 2 in this case, or the 3 will remain if we have disorder in the velocities. Now what we are going to do is to say, okay, we don't have 3 particles, we have n particles. And for example, in this case, we have 10 particles and a final configuration of 3 particles, and the one on the left has 3, the mass is 3, in the middle is 6, and on the top is 1, okay? So a little bit of notation, xn is the number of particles at time t, and I will be interested in studying the number of final particles, that is x n tilde, and the mass vectors. Okay? So, now let's put some hypotheses to the model and say the velocities are random, are IID random variables with some probability law f. And okay, this is the distribution of the last collision that, as you can see, it has criticality. This is the scale version on the right. But the important point here is that this model has been studied previously, and the probability law of observing when you have n particles at time 0 to observe at final k particles is known. Okay, it has this expression, and moreover, the expected number of final particles with mass s is given by 1 over s. Here we have again criticality with an exponent equal 1. So now our question was, given a model, this fusing particles model, can we generate other models within the same class? So in order to simplify the question, what we are going to say is, okay, we know that Xn has this law, and that the expected number of clusters of size S is 1 over S. So what other models belong to the same universality class will be the same to say what other model satisfies these two equations. Okay? Now, V1, V2, Vn are the velocities of the particles that are random. When you have a finite configuration, you just like cluster or pack every group in some way in order not to have new fusions. Okay? So there is a way to know which is the number of final particles and which is the mass of each one without evolving the system. That is this equation. There isn't any detail about which is the function g and m tilde. But the point is, if you give me the m velocities, I can say, okay, there will be 14 final particles, and the mass vector will be this, and this. Okay? So to know which other models, basically what we do is we change this m function. We say, okay, it can be more general. And when we do that, we found some conditions over G, and we found that, for example, all these models satisfy these two equations. This model 1 is the model that is the fusion particle models. Model 0 is another model, model K, okay? And I will show just two of them that it's easy to interpret them. So this is the original model, and model 0 is this one. And what is the model on the left? The model on the left is just a model where when the particle fuse, there is no conservation of momentum. What happens is the minimum velocity is the one that wins. That's why on the left I put traffic jam model on a single line road. Let's think that from here we want to go to Natal, and we have only one line road, and the cars cannot pass. So you will have jumps because some that are in front of you goes at a velocity that is less than the one you want. And the jumps are just these is the same of the mass vector. It has the same probability law. And model 2 can be interpreted in the following way, that is like this. Let's think that you have some particles that you know, I know it's artificial, that you know the velocity of each one at the beginning. So the question is, where I have to put these walls in order to have a gradient of temperature. And for example, here we have 1, 2, 3, 4, 5. 5 groups. These 5 groups, it's the equivalent of having 3 particles here. And the size of each one is how many are trapped in each one. These 3 models have the same scaling. That's why we think that they are in the same universality class. Okay. And finally, I'm going to talk about self-organized criticality. I don't know, somewhere in school talk about self-organized criticality. I think that most know what it is. Okay. I have the Bax-Nepen model, so if there are doubts, you can take it from them. So the Bax-Nepen model is a model where there are n particles that you think that there are species, and each particle is characterized by only one variable that is called the fitness. And the fitness evolve in the following way. You start with uniform fitness, and you change the one that change the one that changed the fitness is the one that is it's the one that has the lowest fitness and also the nearest neighbors. And the idea is the one that has the lowest fitness die, and the neighbors because of this predator and prey behavior. And when they die, they have a new uniform distribution. Okay? So let me show the evolution. You start like this in time 0. This is time 200, 20,000. And here, we reach the equilibrium. If you continue, we will have the same. And as you can see, there is a critical value. There is no control parameter. That's why we think of self-organized criticality and not criticality. And in the case of the Bax-Nepen model, the critical value is unknown, but it's near 2/3. Okay. And this is the avalanche distribution, understanding an avalanche as how many times a death is below the threshold, the critical value. So now I will present a SOC model, but this is a growing SOC model. And this growing SOC model is the following. Let's think that you have 2 minutes, okay. Any axis, okay? The axis is whatever you want. Put biology there. There is a one-dimensional variable. And at each step, a new person appears. And the lowest value person leaves unless the newcomer has the lowest value, in which case no one leaves. Let me show what happens. This is lower, then come other, and then this leaves. Okay? And say blah, blah. And what you obtain with this law is a growing SOC model that have a critical value. if you start with a uniform distribution, you will have that this value is 1 over E, the critical value. It doesn't matter what is the distribution. And if you can think of not the lowest, but the highest, and if you now put here the axis with this, what you have is a participative pricing mechanism. Why? Because what if the community, not the seller, set the price of a product? Let's say I have a product that I want to sell, but I am the seller. I want the community to fix this price, and a mechanism like this can fix a price in. So this is a dynamical auction. Dealers appear at different times, as in a stochastic process, and this is what you obtain. Okay, you obtain a critical, in this case, a price, but it's the same. And the point is the community that fixed that, and there are avalanche and all that. Okay, that's all. Just two things. Based on something that Silvina told me. I work in a small university that is called Universidad de San Andrés. We have some professors that work also in statistics, in methodology, in statistics. And we have a master in data science for if someone is interested in students. And one thing that can be interesting is we have dormies for like 130 people that typically in January and February they are not using, so perhaps there's an opportunity there. And there's some bibliography there.
Okay, so we have time for some questions.
Here. Okay. So you presented these characterization tools in the first part with the graphs that you could use maybe for distinction between healthy and non-healthy brains. Is this being used somehow, or?
Yes, sure. I haven't told you any application, but we have many applications, and we are doing R packages. In terms of application, let me just tell you one example that's part of this dirty rich community of neuroimage, something strange, that we take a large database and we show that if you compare, let's say, there are some public data that have the functional networks and also some characteristic of the patients. And one characteristic of the patients is some volumetric data, for example. The size, how many millimeters has your cortex? Your cortex and mine, they're not equal. They have some difference. So what we did is we separate, like we have a group here that are the ones that have, let's say, some value small in the cortex, middle, and high. And now I think this is our three groups, and the question is, are they different? And we found that they are different. But this poses an important point, because when you are doing neuroimaging, and if it is important, let's say the size of your brain, then typically you say, okay, stay here, you are healthy control, stay here, you are, I don't know, some disease, and you put the people in the scanner. But in order to compare, you need to be well-matched, these groups. And the volumetric variables, you know when they are in the scanner, not before. So this poses a problem, because in order to compare some functional networks, you need to be controlling something that you need before. And we found, for example, we do the same with the amount of sleep. People that sleep less than 6 hours and a half, between 6 hours and a half and 8, and more than 8. And now you say, okay, I think that they are different. Let's test if they are different or not, and that they are different. And nobody say, okay, you are going to the scanner. Okay, let me see, how many hours have you slept? So many results can be like a little bit dirty because of some of these things.
More questions?
And also we use in climate networks.
That's nice, thank you. And just one brief thing. And how does this compare to AI-like methods that you could use also to identify the differences between the...
There is one paper that tried to do that, and our method is like in the first or second position. I'm not sure if the AI can look what is the smallest structure that maximize the difference. But yeah.
Daniel, thank you so much for the talk. I wanted to ask also in the same direction as Pablo asked. When doing this analysis of a sample or an ensemble of networks, how do you solve the computational difficulty of knowing which type of rewiring or each type of labeling of the nodes minimizes the distance between them?
It's a good question. The point is, we think of, for example, brain networks, or I don't know, Twitter networks, where the nodes are well defined. So if the nodes are well defined, there's no problem about that. It's for labeled node.
The best solution is when the problem solves itself.
Okay, so let's thank the speaker again.